Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this is the next video. So this is the third in the trilogy of Boeing 737 flight controls, and this one we'll be dealing with pitch. Things we'll be including, well basically as you can see it's all about the stabiliser and all about the elevators. Once we've covered those two, then we'll go into a little bit of detail about neutral shift. As always, please treat your company training and their manuals as the authoritative source of information. Okay, so big picture overview. The control column moves the elevators using hydraulic system A and or B. If both hydraulic systems fail, then manual reversion is available from either control column. There are also mechanically operated balance tabs linked to the elevators to assist with pitch, particularly useful whilst in manual reversion. The tabs always operate even when the hydraulics are powered. Pitch trim is applied to the stabiliser, primarily to reduce outer trim force on the control column, but it also gives more elevator authority. Okay, so that's the overview. Let's start taking a more detailed look. Alright, first off, the horizontal stabiliser. The first thing you can see in this photograph is that it's got a negative camber. And that's actually true for most airliners, and in fact an awful lot of aircraft. I won't go into the heavy aerodynamics of why that is, but just because the stab has got a negative camber doesn't mean to say it's always giving downforce. I mean, remember it's a function of its angle of attack as well. But as I say, I'll leave that for another presentation. The maximum stabiliser movement, and these are the figures for the NG and the max, are 4.2 degrees leading edge up to 12.9 degrees leading edge down. They're only less than a degree of difference on the other generations, so they're approximately right for all 737s. These positions and the zero position are usually marked on the fuselage, like in the photograph there and the inset photograph up in the top right corner. Pitch trim is applied to the stab, and trim can be applied by either the electric trim switches, autopilot, or the manual trim wheel. So they're your three sources of trim. So stab control, let's see how that's done. This photo I took in the underside of a very early model 737-200, and the reason why I'm using it, well, first off, is it's the same in all generations of 737, so it still looks like that, you know, even in the Max. But the actual location of the hatch is just in a slightly different place on the original, so I was able to get a good, clear, unobstructed view of this, which you can't get in the classics and onwards. So what the view is right up underneath the flight deck floor, at a location just slightly forward of the trim wheel. And what you can see there is a chain on the upper left of the photograph. Looks for all the world like a bicycle chain. I mean, it probably is. Well, probably is the same material. Now that chain is runs from the manual trim wheel to this forward cable drum, which is set at 90 degrees to it, and there's a couple of cogs in there, so they interconnect. And when you move the manual stab trim wheel, the chain turns and the forward cable drum rotates, and that moves the stab trim control cables, those two cables that I've labelled there down toward the bottom of the picture. So that's mechanically how it all works. Now those cables then run back from the flight deck, and you can I've indicated which pair they are in this photograph here. Not the innermost pair, that's the rudder. The next pair out. and they run the full length of the cabin floor. What you can't see on this photograph are the elevator control cables because, as you can see, that particular section of floor there is quite busy, and the elevator cables, like several others in actual fact, have been diverted to route further outboard of this area here. So I can't show you a photo of the elevator control cables, at least not in this location, but we can see them at the back of the aircraft in a later photograph. Now this is the inside the tail cone, looking aft, and the stab trim control cables arrive here. At the bottom of the picture, you can just about see them coming in before they go to that aft cable drum. Now that drum, as that rotates, that engages with the gearbox and it turns the jack screw that you can see running running vertically up the center of the photograph. And on top, or at the upper end of the jack screw in this particular photograph, you've got a large green coloured unit there. That is actually the forward edge of the stabilizer internally. So you've got the horizontal stabs that we know and see on the left and right hand side of the outside of the aircraft. Well, they're connected to this framework here, and that the front of that runs up and down this jack screw as the jack screw turns. Other things you can see on here are the actuator for electric trim, and up on the top right there are limit switches, and they will stop any motion of the stabilizer when it reaches its the various limits, and I'll come on to what those limits are in a later slide. This photograph I actually took at a breaker's yard. It was the only way I could get a good decent photograph of the stabilizer attachment points. So the horizontal stabilizer assembly, as I've already said, it consists of a center section frame, which we saw in the previous photograph. That's inside the fuselage. Now on that frame, you've got these 5 bolt holes which stick out, 5 on the left side and 5 on the right side, and onto that is what the actual left and right stabilizers are bolted onto. Now the rear of that center section is mounted on a hinge, and you can just see where I've indicated that's the axis of the hinge there. The front, as we've already seen a couple of slides ago, is attached to the jack screw, which changes the angle of the stab trim as the trim is applied, and you can see where the 2 bolts are that there's quite a freedom of range of movement there, where the leading edge of the stabilizer is free to move up and down. In actual fact, there's a little bit of movement at the further back where the 3 bolt holes are, but not much because it's quite close to the hinge at that point. Alright, on to stab trim, which is obviously what we use the stabilizer for. Now, you've probably noticed that there are 2 electric trim switches on your control column. What you perhaps may not know is that only one of them is for the direction. It's actually the right hand one, and the left hand one is just an earth return. What the earth return does is it kind of asks you, are you really sure you want to trim? And so the stab will only move if both switches are operated, and what this gives us is protection against spurious electrical signals. So if there was some spurious electrical signal on the direction channel, it wouldn't trim undemanded, because what it needs is a positive verification that you, the pilot, want to trim, and you do that by simultaneously moving the earth return at the same time. Now, if you want, you can actually test this. Next time you're in the flight deck, um, just try moving the two switches simultaneously in the opposite direction. It's a bit tricky to get your thumbs in there, but give it a go, and you can see for yourself which one is the direction, and you know which one is not. You know, is the Earth return. Um, Now, what I must say, as I'm inviting you to experiment here, uh, well, first off, only do this on the ground. Second off, only do this before you've set the stab trim for the takeoff position. Um, but thirdly, don't be tempted to um, the captain apply forward trim at the same time as the FO applies aft trim, because if the trim switches on both yokes are simultaneously applied in opposite directions, it'll engage both the up and down clutches back at the stab motor, and that will result in motor stall. That may overheat the stab trim motor and damage it. So for heaven's sake, please don't try that. You can try on one control column, just try moving these two in opposite directions. That's safe, just to show you that you know which one's the direction. Why you would need to know that, I don't know. It's really just background knowledge, is this. Okay, onto the stab trim wheel. Now you've probably noticed it does turn at different speeds, depending what's going on, and they are as follows. So for main electric trim operation, so that's you using the stab trim switches on the yoke. With flaps up, it'll turn at 0.2 units per second. Flaps not up, it'll go twice as fast at 0.4 units a second. With the autopilot, it's altogether slower still by around about a half, and flaps up, as you can see, 0.09 units a second, flaps not up 0.27 units a second. So it's slower with the autopilot than with the trim switches. And of course, if you wish to move the trim wheel manually, then you can move that at whatever speed you wish, although it is actually quite slow to turn. The stab trim range and takeoff green band actually varies slightly with the aircraft series. Now, not a lot, but a little bit. And you can see I've just collected together some photographs from each of the generations. The green band actually changes for the individual series within a generation as well, but again, not very much. But you can see it's roughly around about the 2 to 3 to just over 8 mark, again depending on which series. Boeing in their wisdom decided to take away the max CFG position, or the takeoff CFG position, from the classics onwards. Not sure why they did that. I think folk have been trying to work out the max CFG in the cruise, and it's not quite as straightforward as reading it. This was only valid for takeoff. You can see the correlation with the actual stabilizer position on the photo above. So 0 units is 4 degrees of stab nose up, in other words, aircraft nose down. 4 units is stab neutral, and 17 units is full stabilizer nose down, or in other words, aircraft nose up. All right, I said I'd mention the actual stab trim authority, and here it is. It's all kind of summarised in this table here. Basically, it varies according to the aircraft series, flat position, and even the method of trim. Full trim is only available with the manual trim wheel. That overrides everything. But I will say, if you've got yourself into an extreme trim setting that's beyond the electric trim range, electric trim can be used to return the trim back into the normal range. And again, this is something you can try for yourself safely on the ground on a turnaround. If you manually trim out of range of electric trim, you can use the electric trim to bring it back into range. The trim range is also increased for shorter fuselage aircraft because the horizontal stab is the same on all models, but the moment arm obviously reduces with the shorter fuselages. As I say, it's all summarised on that table there, and you can see that I've kind of put the hierarchy of increasing trim range from left to right. So the narrowest trim range is electric trim with flap, then electric trim with clean, then the autopilot, and then manual trim. The stab trim light, this was actually only fitted to the originals, and all it does, it tells you that the main electric trim motor is operating. I've no idea why they thought they would need this light, because as we all know, the noise from the trim wheel when it's turning is enough to tell you that it's operating. But I guess they thought people would need another cue. Little point of trivia on the originals and the classics. The stab trim control wheels should be mounted with their white marks, which actually are not visible on this. 90 degrees plus or minus 15 degrees apart from the other wheel, so that in the event that the trim wheel handles need to be used, one handle will always be in an accessible position. They dropped the requirement for this on the NG or the Max, so the white marks and the trim wheel handles can be mounted anywhere now. All right, the stab trim cutout switches. This actually came to light with the Max accidents, that there been a slight change of logic with them. All generations prior to the Max had separate stabilizer modes cutout switches for the main electric trim switches. Again, they're the ones on the yoke, and the autopilot trim. And these switches you'd be directed to use from the QRH in the event of a stab trim runaway. There isn't actually a procedure which calls for them to be used individually, but if you're troubleshooting, if you need to, then on all generations prior to the Max, you were able to isolate one or the other. On the Max, they combine them, and either switch will activate both main electric autopilot and also, of course, as came to light, speed trim and MCAS, they stab trim inputs. And the two switches are simply there for redundancy. Their functionality is actually identical. Just a reminder that manual stab trim is always available, even if both of these switches are in the cutout position. Again, I'm sure you all know that, but it never hurts just to be reminded of these things. Manual stab trim will override anything. It's always available as long as there's a cable linkage to the back. The stab trim override switch. Now this, in my experience, is often forgotten by folk because we very rarely have to use it. Although, as I'll tell you in a moment, I did have to use it in anger on a real revenue flight once. Now this, you can kind of think of it as almost being the opposite of the stab trim cutout switches. So the stab trim cutout switches you would use to stop a stab trim runaway. This you will actually use to permit stab trim if it's not available to you. Now there is a stab trim override mechanism underneath the control columns, and what this does is, if you are trimming forward electrically and you move the control column aft, the electric trim will stop, and vice versa. So if you trim back and and simultaneously move the control column forwards, the electric trim will stop. When you move this stab trim override switch to override, then that control column cutout function is disabled, and you can use electric trim regardless of where you're holding the control column. And this could be used to control the pitch of the aircraft with trim, say in the event of a jammed elevator or misbehaving a misbehaving trimmer. And this was the event that happened to me. So I was flying a 737 into Madrid, as I recall. I disengaged the autopilot on the approach, and after a little while, I found I needed some trim. So I trimmed forward, and then maybe I needed to trim back. But I found that I wasn't able to trim back electrically. I could trim forward, but not back. So of course, as it's dawning on you that you don't have back trim, and you're just moving the switch forward and aft to try and check what functionality is remaining. The aircraft, of course, is getting more and more nose heavy. I gave control to the FO for a moment to see if he could trim back, and he couldn't, so I took it back. And fortunately, I remembered this switch here. I moved the switch to override, and my stab trim was fully restored. I have to say that was the only time that ever happened to me in about 20 years of flying 737s. But there you go. It was a good one to have up your sleeve. This again you can safely test on your next turnaround. Again, please don't do it. Well, please don't do it in flight. Please don't do it if you've already set the stab for takeoff. So at an early stage in the turnaround, try it. Try moving the control column forwards, and then trimming aft. And you know you won't be able to. If you move the stab trim switch to override, you will be able to. It's probably good value, everybody doing this, if for no other reason than just to remind you of its functionality. I mean, if nothing else, to remind you where the switch is. I mean, it's actually at the rear right corner of the aft electronics panel. But you know, if I were to ask you to say where is this switch, I bet a few of you would struggle to remember. Anyway, there it is, and I guess that's one of the benefits of these videos for everybody, that it just helps us, you know, to remember these little used functions. All right, that's enough of stab. On to elevators. The elevator authority we'll talk about first. Now, the elevators are down rigged 4 degrees from the stab chord line, so they droop. And they droop, and that gives the whole stab and elevator more camber, which gives it a little bit of lift, which probably answers some of the earlier questions you had about the negative camber on the stab itself. So from this 4 degrees down position, the elevator can move a total of 24.3 degrees up and about 18 degrees nose down. So it's almost full authority up and down from that position. It's not quite, but it's absolutely enough for almost any scenario. Now you can see in this zoom photo I took of the back of the aircraft that there's a datum plate on each side. And these are there to show the engineers the neutral position for rigging. There's also one on the tail cone for the rudder as well. The elevators don't. The ailerons don't have them, but the elevators and the rudder do. Now, trust me, I've seen engineers do this, and rigging the elevator and the elevator tabs is a real difficult fine-tuning job, and this plate is put there to help them do that. Balance panels, let's talk about those. Now, for those of you that didn't see my presentation on roll, I think it was, where I featured these with the ailerons, let me just recap quickly on the function of balance panels. So we got balance panels on the elevator, actually located within the stab. These have got balanced weights as well, and these assist with elevator movement and help harmonize the controls, which is always nice. And these are particularly useful in the event of manual reversion. They take a lot of weight out of the flying in manual reversion. and I say I've done an awful lot of actual manual reversion flying in the aircraft. Now I can say that it is well harmonized and well, I won't say light on the controls, but it's very, very manageable, very manageable. The air pressure actually enters a little vent which is quite hard to see from below on the well, or above, if it's whichever side is the high pressure side, depends on the deflection of the elevators. While on the opposite side, air is drawn out of the vent on the low pressure side, and that pulls the balance panel with it. As that panel is connected to the elevator, then it helps actually move the elevator as well. Okay, so there it is. You've seen those diagrams before with ailerons, but let me actually show you them, what you're looking at in real life, because it's only on the elevators that you can that I've been able to see these things. And there they are. I've circled them in red. These are your 3 balance panels on each side. I say they're not normally visible, but I managed to grab this photograph taken during heavy maintenance of one of our 737s, and you can see the panels there. And I'll show you a better photograph now, taken from directly underneath. And you can see the left 2 panels there. You've got the balance panels in green, and the white parts there are actually the extension of the elevator, the elevator nose, if you will. So that's where they connect. You can just about see some little rectangle shapes, a couple of green ones on the left and a white one on there. They're the adjustable weights. They're the ones that the engineers use to again stop any flutter or what have you, and that might happen after painting of the or removal or damage repairs of the elevator or the tabs. You can see there's actually no balance panel in the next over position. Okay, onto the tabs. The tab, obviously, that little bit right at the back there. Now, these on the originals, that's the 1 and 200 series, they're normally faired with the elevators, so that they just stay fixed in to the elevator position. But they become alive during manual reversion to move in the opposite direction of the elevators to assist their movement. So they become balance tabs during manual reversion, as in fact they do on every generation of 737. On the classics, there was a slight change of plan, and the elevator tabs always functioned of balance tabs as balance tabs, regardless of whether you're in manual reversion or hydraulics normal. On the NG and the MAX, the logic was changed yet again. This time, the tabs are normally balance tabs. That's when the hydraulics are normal and the flaps are up, but they become anti-balance tabs when the flaps are not up. And this is to make the aircraft less sensitive in pitch with flap. But I should say that during manual reversion, the tabs change back again to become balance tabs regardless of flap position to assist with pitch control. So, and again, I've summarised it, the logic changes with the generations in that table down there at the bottom right. All right, so let's have a look at that. A picture's 100 times better than a table. So what I've got here is a series of photographs that I took. I got my FO to hold these configurations for me while I took photographs, and I'm actually quite pleased I did now, because I'm able to show you these things. So this was in a 737NG. I can't remember which one, but they all behave the same. And I got the FO to hold full aft elevator, so with the control column full aft, and you can see that the tabs are acting as balance tabs here. So as the elevators go up, the tabs are coming down to assist the movement, and that's what you get on an NG with flaps up or manual reversion. I then got the FO to extend the flap just to 1, And what happened was the tabs reversed position, as you can see here. So this again is it's hydraulics on. The only difference between the two photographs is that in this second photograph, the flap there was some flap extended. Then what I did next was I got the FO to, on the flight controls panel, move the A system hydraulics to standby rudder, and see if you can guess what happened to the tabs when he did that. I'll give you a second. So what I'm saying is, with the flaps not up, hydraulics normal, so as per picture 2, I got the FO to move the A switch on the flight controls panel to standby rudder. Okay, here it is. What happened was, on the left-hand side, on the left-hand elevator, that tab went into balance tab mode because it said, hey, I'm in manual reversion, you want me in balance tab. But because the B system wasn't in standby rudder, that remained in anti-balance tab mode. Now, I can tell you again, because I've done this in flight, it doesn't actually give you any significant, well, any detectable actually unwanted roll, as the elevator and the tab deflections are usually quite moderate, particularly when you're with a hydraulic system down or in manual reversion. But I just thought that was interesting, and a great demonstration of the functionality. The elevator tab mechanism itself, these are mechanically driven by the movement of the elevator against the stabilizer. So it looks for a difference in elevator position from stab to move the tabs. So you've got one end of a bell crank attached to the stab, the other's attached to the tab push rods. So as the elevator moves, the tabs move in the opposite direction. Now these photos are actually taken on classics, with the tab removed, as you can see on the bottom photo. All of the generations, the original NG and Max, the mechanism is actually more complicated to enable either a movement or reversal under manual reversion. And those systems use a solenoid-held actuator against springs on the crank. But the classics was actually the easy one because the functionality is the same, come what may. So that was the easy one to show. You'll recall that I mentioned on the which presentation was it? The one of the other flight control presentations, pitch it was, about this bulletin 19, which hopefully you has been removed from all your FCOMs now, which prohibited the use of speed brake above 310 knots due to vibrations in the elevator tabs. I mentioned it in that presentation, but what the bit I just kind of add to the story here is the hinges. The original unmodified aircraft were as shown at the bottom photograph. They're 4-hinge aircraft, four hinge tabs. When the modifications were complete, the modification put 6 hinges on there. And what I'm showing you in those bottom 2 photos is the difference between the 4 and the 6 hinge. In other words, how to tell from the ground or on your walk around whether you need to be obeying this speed brake speed limitation. As I say, you shouldn't find this. I mean, all companies should have had this done by now, but you never know. I mean, there are thousands of these aircraft built, so you may come across one. On to elevator control. Again, we got this great little photo, which you may remember from a previous presentation, but I'm going to use it again because it shows everything we need to see here. So we are under the control columns, looking up and slightly aft, so forwards is to the top of the picture. And what we've got on the left and right hand side, those sort of circle metals, spherical shape or cylindrical shapes, they are the base of the FOs and the captain's control columns. They are interconnected by this elevator forward input torque tube, which you see there running across the picture left to right. Now, below that, you can see hanging down a pair of elevator balance weights. These are to counteract the weight of the control column, just to harmonize the input of the controls. You've got one on either side because, don't forget, in the event of a jam, you can override and move this input torque tube independently. That's why there's one of those on each side. The rest of this we can see. Let's start down at the bottom where you've got two forward control quadrants there. What I want you to notice is that unusually for control quadrants, they are dual quadrants. So you can actually see that there are two lines or two channels there for cables to run in. So looking at well, say the left-hand side there, on the inboard section, the cable actually the elevator input cable, it goes forward, it goes around a pulley, and then it comes back the other side of the weight and goes aft down the cabin. On the outboard section of the quadrant, there's another cable, a second cable, and that just runs straight aft. It's a little difficult to see on these photos, but it is there. Perhaps if you pause the video and zoom in, you might be able to see it. But my point here is that there are a total of 4 cables. So it's not a single loop. It's actually 4 cables, and that is an extra level of redundancy. So if a cable should break or jam or what have you, or anything should happen, you've still got a cable to have some level of control. I mentioned the breakout mechanism, the possible independent movement of the controls in the event of a jam. I've highlighted it there where it is, so that's where the breakout mechanism lies, and this is an enlargement of that area of the photograph there. So what this does is it will separate the left and right sides of the input torque tube, and that allows elevator control if one column has a jam. Now the breakout mechanism, it's a cam roller type, and you can see it. I've labelled it up on the photograph. You can see the cam inside that sort of butterfly shaped roller there. The cam is connected to the captain's torque tube, and the roller is connected to an arm of the FO's torque tube. So the 2 springs hold that roller in the detemp position. It'll take about 31 pounds of additional force to extend the springs during a jam, which isn't much, but it will take about 100 pounds of force to move the elevator 4 degrees, which is around about quarter travel. Now, this is enough for a flare, but it's significantly heavier than the manual reversion. So those of you who've done manual reversion in the sim, or lucky enough to have experienced it for real, it's fairly heavy on the controls. But if you do get an elevator jam and you have to go in independent operational and control column, then be prepared to have a bit of a workout, because it is quite heavy. I think from memory that I know that there are other breakout mechanisms further aft on the aircraft, out near the elevators, and I'll come on to show you those. But from memory, the breakout loads on those partner, I think it's the stab input rods to the elevator, it's around about 90 pounds each. So you're looking at about 180 pounds of force to overcome a jam if it happens in the rear section of the aircraft. So definitely a little bit of strength required there. which of course was addressed in the Max. The elevator jam landing assist, and again, I've covered this in the Max differences video, but it actually sits in here quite nicely. As I've written, it gives limited changes to the vertical flight path from the spoilers to assist the approach and landing if the normal elevator system jams. And the reason why they've put this on is A, because they could, because we've got fly-by-wire spoilers on the Max, but B, because it really is necessary. If the worst should happen and you've got a jam at the back, you're talking about 180 pounds of breakout force to move the elevators independently, which is a lot. So you just got to reach up now, flick the elevator jam landing assist, and you will get assistance from the spoiler panels, which is a fantastic function. If only it could be retrofitted to all the other generations, but of course it can't. Alright, so moving further back down the aircraft, this is now in the tail cone looking forwards. The 4 elevator input cables, which I spoke about earlier, they terminate at 4 control quadrants. The FOs and captains up and down quadrants, so there's one for each. And if you look down at the bottom of the photograph, you can see that there are 4 quarter quadrants there. Now, they are attached to the input torque tube, and they, as inputs are made on the controls, it's transmitted by the cables and turned into a rotation of that elevator input torque tube. The other thing that can act on that input torque tube are the autopilots, and this, again, for those of you that saw my my wheel well hydraulic tour, will recognise the similarity of those two autopilot actuators. The arrangement is very, very similar to that on the ailerons, but just turned through 90 degrees. So you've got the actuators for the A and B autopilots. They move or can act in series on dual autopilot to move the elevator autopilot input crank, that long tube there on left of center, which is attached. That's not really an input crank. It's a sort of control rod, and it goes down to the input crank, which is on the input torque tube. So that's the second way of putting inputs into the elevator input torque tube. The other inputs will actually come from, and if I start sort of left or top right hand corner there, you got the Mac trim actuator, the feel and centering unit, the elevator feel actuator, and all 3 of those act through the elevator feel and centering input crank to again give inputs to the elevator input torque tube. These inputs, you should bear in mind, they also backdrive the control quadrants, so they will not only cause the elevators to move, but they will cause the control column to move as well. And this is useful for us as the pilots, because that gives us some feedback that the elevators are moving. Alright, so how does the motion get from the input torque tube to the elevators? Well, this is how it does it. Now, what I've done on the right hand side, I've labelled the components. On the left hand side, the components are the same, but just the left components. So what I've done is I've shown the flow of travel on the left hand side. So let's start from the bottom to the elevator input torque tube. Now, again, you've got inputs from various sources, either the control column, the autopilot, or the elevator feel and centering unit. That will rotate that elevator input torque tube. There is then a rod, one on each side, out on the outboard section there for your left and right elevator inputs. They go up to the PCUs, which you can see sort of center picture. The PCUs hydraulically controlled, so they change that manual input and well, magnify. They use hydraulic power to move the output torque tube, which rotates, and the elevators are attached to that output torque tube, and that rotates the elevators, causing them to move. Remember, the elevators will move with either hydraulic system. So if you've lost a hydraulic system, you've still got elevators from the remaining hydraulic system and the remaining PCU. Outside of the aircraft again, this is what you see. So I've labelled at the top there the end of the output torque tube. So the top of the previous picture, that was the output torque tube. That's where it is. You can see below that a crank coming off it, and then the elevator control rod there, which is the rod that is physically attached to the elevator. And that, of course, lies inside the inside the stabilizer. Obviously, you don't normally see this. This is a photograph of an aircraft taken with the stab and elevators off. So that's how it works mechanically. Anyway, so let's have a closer look at elevator feel. Now, elevator feel, unlike the aileron feel and the rudder feel, which is done with springs, elevator feel is hydraulic, and it's controlled by a computer. Now, this computer is not the sort of computer that that you'll find in the E&E bay. It's not the sort of computer that if you were to tell anybody under the age of, I don't know, 50, would suggest to them was a computer. This is a computer that was designed in the 60s, and there it is on the on that bulkhead wall. It's a computer without electrics. It's, if you like, a hydromechanical barometric computer. It sends metered hydraulic pressure output to the dual field actuator on the elevator field and centering unit. That's what it does. But it takes inputs. The raw input is the hydraulic A and B system, and what it does via a series of inputs, it modulates the amount of hydraulic pressure that comes out of that, and that is used to give us feel on the control column. So let's have a look at the inputs to this computer. There are 3 inputs to the elevator field computer. The first you probably know. It's the elevator pitot probes up there on the fin. Now, since feel must increase with airspeed, that's logical. That's what it does on conventional, or light aircraft. The controls get heavier with airspeed. That's what Boeing's trying to replicate for us, and this is how it does it. It's put 2 dedicated elevator pitot probes up there on the fin to sense local airflow, because they're as near to the elevators as they can without interfering with it. They connect to Q diaphragms, which you can see down there on the computer, and they regulate the A and B hydraulic pressure. Okay, so far so good. The next input you're probably not aware of, and this is the Q field gets an input from the stabilizer position. So feel will increase with displacement from the stab. And again, if you stop and think about it, this is logical. The more you displace, the more you move the control column, you're displacing the elevators into the airflow, and that is what this part is trying to replicate. So it needs an input from stab position, i.e. away from datum, and the stab position it's done via a control rod, which you can see there, that small vertical yellowy brown coloured rod there, and that is attached to, you may remember from the earlier photo, that large unit behind it, that is the the front of the stabiliser that's attached to the jack screw. So as the stabiliser moves up and down on the jack screw, so that rod moves up and down, and so that moves that lever on the side of the elevator field computer, and so it regulates the hydraulic output from the computer, and so it gives us a change of feel on the flight controls. The third input is from the SMID. It's the elevator field shift module. Now, the SMID, clever little computer that it is, it says, right, you're approaching a stall. You really don't want to be pulling any further back on the controls. I'm going to give you a little bit of assistance. It's effectively a stick nudger, but by another name or by another mechanism. And what it does is, as you approach the stall, it gives you up to 850 psi hydraulic A system pressure into the elevator field computer to increase the field force on the flight controls. So there are your three inputs to the elevator field computer. Now, I'll just take this opportunity to mention the field differential pressure light, because that's how we see it in the flight deck. That really is our only or our most obvious manifestation of it. I mean, we kind of forget, really, I think, that what we're feeling through the control column is actually artificial feel. But it is. Anywho, the field differential pressure light, this will illuminate if there's a difference of 25% or more between the hydraulic A and hydraulic B metered, the output from the elevator field computer pressure, for more than 30 seconds. And this is usually if you've either lost a hydraulic system or an elevator pitot probe becomes blocked. Should say that even if either of those things do occur, the elevator field system will continue to function on a single hydraulic system. The only thing you may lose is if it's the A system that you've lost. You can't have that input from the SMID. But if it's B system you've lost, you won't know it, and you'll still have the extra stall protection there. Okay, so the elevator field and centering unit. It's one of those blocks on the schematic in the FCOM. In actual fact, the FCOM schematic, I think for pitch control, is actually quite good. So you may be relieved to hear that I haven't done a schematic for this presentation. Really, I point you in the direction of the one in the FCOM, because it does cover things quite well. So the field force is provided by the field and centering unit. Now, the clues in the name here. This unit not only deals with elevator field, but it deals with centering as well. Now, field I've already explained. That's done by the three inputs to the elevator field computer. But let's have a little look at centering. So well, first of all, the elevator field force from the elevator computer comes into that silver unit below there. That's the dual field actuator. That acts on the input torque tube, and it passes the field back down the cables to the control column. And the field and centering unit has got the following inputs. First one is from the elevator field computer. As I've already said, that this comes into the dual field actuator, which is that silver coloured actuator underneath the unit. This adds a variable field force to the spring force that's within the field and centering unit. The next input is from the flight control computer, and these inputs go electrically. So it's one of the few things on this whole system that isn't mechanical. It gets electrical inputs from the flight control computer, and they go directly to the Mac trim actuator, which sits on top of the field and centering unit. And the last input is from the stabilizer. Now, stabilizer inputs go through the elevator neutral shift rods to the Mac trim actuator, and you can just about see one. They are difficult to see. They're kind of buried behind this unit. I couldn't really get a particularly good photograph to show these rods. Now the stab and the FCC inputs collectively are known as neutral shift. So it's, or if you like, centering. And this is how the unit gets its name. So it's elevator feel, so it's all of the three inputs from the elevator field computer, and then inputs from the FCC and the stab, which are for centering, which we as pilots know as neutral shift. So let's dissect neutral shift. Now, neutral shift, it's the automatic adjustment of the elevator, and hence control column neutral position. What it does is it reduces the force on the control column, it reduces the amount of trim required, and it gives more elevator control. So it does a lot of good things. As I've already said, it'll occur in response to two different inputs, stab position and flight control computer demands. Now what I'd like you to do is just remember, I did mention it earlier, but let me mention it again, because you'll need this to follow what's about to come next. The elevators are downrigged 4 degrees when the stab is at its neutral position, which is, so when the stab's neutral, i.e. 4 units up, the elevators will be 4 degrees, sorry, down. Right, into a graph. This graph is showing you elevator angle on the x-axis there versus stab angle. Now, if you look at the markings of it, elevator angle, it actually goes from negative at the top to positive at the bottom, even though it's elevated down. So perhaps a little confusing, but there is logic to it. And the stab is the angle in units. So it runs from 0 units to 17, or actually 18 is the end of the chart, units. But remember that the angle of the stab is 0 at 4 units. So I've highlighted on there a stab neutral line and an elevator's third with the stab line. The red circle is where the elevators are when the stab is at its neutral position, because the elevators are downrigged 4 degrees. So that's kind of your datum point. Okay, stabilizer neutral shift. That is what's drawn on there in the blue dotted line is the effect of stabilizer controlled neutral shift. And this will move the elevators up whenever the stabilizer moves either up or down to reduce the displacement of the elevators from the stabilizer. And why it does this is to maximize the available elevator range during transient motion. So whether you move the stabilizer or up or down, i.e. you trim nose up or nose down, when that happens, or the elevators will move up according to that graph there. That is stabilizer neutral shift. Okay, let's have a look at flight control shift. So, flight control neutral shift. This moves the elevator neutral position to give more elevator control during takeoff and landings, or strictly speaking, it's whenever you've got flaps out, which Boeing assumed would be during takeoff and landing. Now, it's active whenever the trailing edge flaps are not up and either engine M1's more than 18%. In other words, the engines are running. And it'll operate when either the captain's or the FO's stab switches are operated. Interestingly, not the manual trim wheel or the autopilot trim, but just the electric stab trim switches. Or a flap setting, that the flap setting is changed. So this again is looking at transient changes of trim, and it is trying to give you full elevator authority throughout those trim changes. Right, the graph there, the movement of FCC neutral shift looks a little bit complicated, so I'll take you through it in stages. Let's break this down. So, first of all, for aft CFG operations. Now, elevator downrig is gradually removed with increasing aft CFG, and this is to give you more nose-up control. That's what it's doing. So it's removing that downrig. It's bringing the elevators back up to the third position with the stabilizer. Whenever you've got the elevators third, you've got the full range of travel available to you. Okay. Forward CFG takeoffs. Now this is the common one. This is kind of what it was mainly designed for. Now, elevator downrig is added here by, as you can see, about 1.5 degrees. Now, the increased aircraft nose-up takeoff stab settings, they will give increased control during the takeoff. So again, what you're getting here is increased control for having this extra downrig added. And the control is what they're anticipating that you will need during takeoff. So I say it's even more downrig than usual. Okay, and the last part, and this is really cute. This is for forward CFG landings. And what Boeing have actually done here is that they have removed the elevator downrig, and in fact they've gone further than that. They've actually added some uprig. So they've completely reversed what happens at all other times of flight. And why they've done this is to reduce the amount of nose-up stab trim required. In doing so, in doing that, that will decrease the stabilizer angle of attack. If you're decreasing the stabilizer angle of attack, you're decreasing the potential for buffet on it. You're decreasing the potential for the stab to stall. If there were, and the only time that would ever be likely to happen would be if there was any ice accretion on the stabilizer. So that's what that's all about. So say forward CG landings, the downrig is completely removed, uprig is added, so that you're reducing the stab alpha to reduce the chance of the stab stalling. Okay, if you put the flight control computer neutral shift and add that as the elevator field and centering unit does, add that to the stab control neutral shift, what you get is the total elevator neutral shift, and that's what I've shown there on the red line, and that's what we get in flight. Now remember that the FCC neutral shift is only active when you've got flap. So for most phases of flight, you can ignore that. All you will get will be the curve of the stab control neutral shift. But for takeoffs and landings, at any time that there's flap, particularly with changes of flap, particularly with electric stab input, then that's what you will get. The changes as shown in the red line there. Okay, by way of demonstration of this, you can actually see neutral shift in action. You may not have noticed it, but you will have seen it every flight. And this is when you select the takeoff flap in the before taxi procedure. We've got a video clip here, which was sent to me by Captain Asiri, who's kindly filmed this, because I haven't had a chance to. remember the two criterion for activation are that an engine must be running and flap. So it's going to react to stab trim or a change of flap. So when you select take off flap, you will see the control column move forward approximately 1 centimeter. And this is the realization, the visualization, if you like, of neutral shift. All right, so the mechanics of it. Again, we've kind of covered this before, but more specifically for the neutral shift function. So the stab moves the two elevator neutral shift rods, which you can just about see at the top of the picture. That provides an input to the elevators through the Mac trim actuator. The flight control computers send electrical signals to provide input to the elevators also through the Mac trim actuator. When that Mac trim actuator moves, a mechanical input goes through the field and centering unit to the input torque tube. This through the PCUs, and the output torque tube will move the elevators, and through the input torque tube and the control cables will move the control columns to the new neutral position. So the elevators will move, and your control columns will move. So everything's in harmony. You can see what's happening, as per the demonstration on that previous video. Okay, now I realise that there's a lot of things that we've covered on this, and there's actually fairly widespread confusion on the line as to these four functions. So let me just spell out the difference between feel, neutral shift, speed trim, and Mac trim. And I should say speed trim and Mac trim I haven't covered here, and I won't cover it here because you probably had enough to take in already, but I will cover those two in more detail in the autoflight presentation. But just to summarize, just to spell it out, feel acts on the elevators to give a control column force that simulates aerodynamic forces. That's what feel is. And this is necessary because the elevators are hydraulically powered. Neutral shift acts on the elevators to reduce the control column force necessary to trim the aircraft. It's mainly during initial climb out after takeoff with a forward CG with the engines operating. Speed trim automatically applies stab trim to give positive speed stability. And this is to improve handling during operations at a low gross weight, aft CG, high thrust when the autopilot's not engaged. So when you're manually flying it right back in the bottom corner of the envelope, it will increase control column forces, so that if you release the control column or ease your pressure on it, the aircraft will naturally return back to the trim speed. That's what speed trim is. This operates anywhere between 100 knots and 0.68. And finally, Mac trim. This moves the elevators to prevent Mac tuck. And this is active between 0.615 and 0.86. Once again, let me just say that I'll cover speed trim and Mac trim in more detail in a subsequent presentation. But that right there, that's your summary of those different factors. If you enjoyed this video, don't forget to give it a like, subscribe to my channel if you haven't already done so, and please tell your colleagues. Thank you. That's it from me. If you've enjoyed this video, please like, subscribe, and share it amongst your colleagues. Thanks very much for listening.